Okay, welcome to the class. What we are going to learn today is the receiver design. Okay, for the transmit chain we have learnt. So what we have covered till now is basically the PDSCH transmit chain, and this becomes the PDSCH receiver chain. Okay, and just to complete the understanding, okay, where will PDSCH transmitter chain be implemented? It will be implemented on the base station. Okay, or the downlink transmitter chain. Who is the transmitter in the downlink? Base station. And who is the receiver in the downlink? UE. Okay, so what we are learning here is basically the UE processing now. So that was the base station processing, whatever we have learned till now, and we are going to learn the UE processing. Okay, this is only one part of the UE processing. It is much more complicated than what I'll show you. Okay, because UE needs to do lot many more things before it can actually do this. Okay, but hopefully when those modules have been implemented, they have been executed. Okay, so you have reached the stage wherein like you have to process the data. Okay, so we'll touch upon all that. Okay. So this basically, this receiver design for the transmitter chain which is discussed, that is PDSCH chain. Okay, and then we are going to see the PDSCH receiver chain. So similarly, there is this base station transmitter. If it is uplink, okay, what happens? That is called the PUSCH chain. Okay, and physical uplink shared channel. Okay, this part of the processing, whatever we have learned, is more or less similar in both these chains. Okay, right, whether it's PDSCH chain or PUSCH chain. Okay, so this part, whatever I showed you, okay, let's come here. Okay, before we actually get into this PDSCH receiver, this part, okay, this is PDSCH transmitter. Okay, this becomes PDSCH receiver. Okay, so this basically is the split. Okay, this is base station, this is the UE. Okay, now if you flip it, okay, if you are to start talking about the uplink, okay, then this part of the chain remains same. Okay, there are other modules which come which will be different. Okay, so then if it is PUSCH transmitter, who will implement this? UE will implement this, and then this will be implemented by the base station. Okay, right? So please understand this. Now, where will the transmitter chain begins from raw data? It ends at the modulated symbols. The PDSCH receiver chain, where will this begin? Begin from the demodulation, and then it has to give you this, the raw data. Okay, that's the process. It's the reverse of what you have learned of the transmitter. Correct? Okay, so we begin from here. Okay, so we understand what kind of modulation schemes standard gives. Standard gives these modulation schemes starting from 4 to 256 QAM. Okay, now it has to be demodulated. These QAM symbols need to be demodulated because that's what we are seeing. Okay, so and what is the job of this demodulation? What should it do? Okay, demodulation should basically look at these symbols because modulated symbols. Okay, we saw that. Okay, if it is QPSK, there will be 4 possible symbols. If it is 16 QAM, there will be 16 possible symbols. Okay, and now the question you could ask is, okay, if the mapping at the modulation is so clear, what is the job of the demodulation? Okay, right? So we'll see that. Okay, so why demodulation is complicated than modulation? Okay, because demodulation has to decide. Okay, and it has to decide based on what kind of received signal it is, based on what kind of signal it is receiving. Okay, so that's what is the job. Demodulator detects bits from these modulated symbols. Okay, right? And now you could ask me this, okay, that LDPC decoder, okay, works on the demodulated bits and not on the symbols. We discussed this briefly in some form. Okay, now you could actually have a LDPC decoder working on symbols directly. Okay, now why it is not done? Again, because of the implementation constraint, not practical to design decoder for different modulation schemes. Okay, 4 different modulators, you'll have 4 different demodulators, 4 different decoders also. Okay, so in practice people do that, not in the standard, but if you want to implement some other simpler communication systems, okay, you can take directly the demodulate the symbols, and then you can feed them to the LDPC decoder. Okay, it will work. So, but not practical to design. So that's why basically this demodulation is there, so that it gives you bits. Okay. So now what is happening? Okay, we'll take an example of QPSK demodulation. These were the 4 constellation points. You transmitted one of them. If you're right, okay. If you look only at one symbol, okay, right. Let's say you transmitted one of them. What happens here? You will not receive exactly one of them. Why? Because what is the reason? Okay, how did your channel look like, or how did your system look like? Okay, right? You transmitted, if X is the modulated symbol, what kind of transformation it undergoes? It gets multiplied by H, which is complex. It gets added by the noise gets added. Okay, right? So what happens? Let's say you transmitted one of these points. You will. Okay. Now depending on what H is, okay, let's say H is, you are in the basement of a building, H becomes very poor, H becomes 0. It can, okay, right? H becomes very low. What will happen? You transmitted X, it becomes 0. Right? Okay. Forget if H is also not there, okay, and then if H is 1, just H is very strong, okay, if only noise is there, okay, right? So you're there in a poor SNR regime. What is SNR? The signal power is much lower than ratio of signal power to the noise power. If noise power is very high when compared with signal power, okay, what will happen? You transmitted this, it will move here, or it might move here also. Fine. That's how your communication channel is. Okay. Now, if this noise is not there, you don't get your jobs as an engineer. Okay. Why? Because whatever you are transmitting, you are receiving without errors. Why will you need LDPC encoders? Why will you need all these encoders or decoders, sophisticated processing? Right? So we have our jobs because noise is there and the channel is there. Okay. Right? So now what is the job of this QPSK demodulator? It looks at this received symbol. Okay, this is what it has received. Okay. Now based on this, it has to decide which of this point was transmitted. Correct? Okay, if it can decide, then what will it do? If it decides that this was the point which was transmitted, then you know that this basically it is easy to demap this constellation point to these bits, because that mapping you know, right? Okay. So what I am saying here when I say that mapping you know is basically this constellation is known at the receiver also. Okay. It is not known what was transmitted. Okay. Correct. So what I am going to tell you a very simple rule. Okay. This comes from the communication theory. Okay. And what is this rule? This is called, in order to detect the bits from the symbols. Okay. Right. What do? You apply something called this nearest distance detection rule. What is this? Okay, in this case, okay, you will compute this distance of this received point from all these transmit points. Okay, right? And whichever point gives you the minimum distance, you declare that as transmitted point. Okay, right? And one can show you that this is the best you can do. Okay, right? Best in terms of reducing the error. Okay, the best has to be defined appropriately. Okay, so this decision rule basically gives you minimizes the bit errors. Okay, now once you have basically decided based on this minimum distance rule, okay, right, that this was the point which was transmitted, then you do the reverse mapping. Okay, do you understand this? Okay, first is basically apply the minimum distance rule, and then threshold. So once you have decided this minimum distance, you basically, what will you say? Okay, you will declare it, you will threshold it to that this point was transmitted. Okay, once you have declared that this point is transmitted, then it is easy to do the reverse mapping. Now keep this in mind that, okay, this is the final point, demap the symbols into bits once this is decided. Okay, now I am taking a liberty and while telling you this, okay, this is something called the hard decoding. Okay, wherein what we are doing here is we receive this point and we are thresholding it to, we are declaring that this was the point which was transmitted, okay, or whether this was transmitted. We are deciding, okay, at this stage itself. Okay, this is called hard decision decoding. If time permits, I will teach you about soft decision decoding also, wherein you don't decide like this. Okay, you calculate the probability of whether this symbol was transmitted, or this symbol was transmitted, or this symbol was transmitted, or this symbol was transmitted. Okay, right. So in this class, I am not going to do that. Okay, that, like the soft decoding is better than this hard decoding. Okay, it gives you performance gains. Okay, we'll see that later. Okay, now, but for this class, what are we doing? What is demodulator doing? Okay, it is taking in these symbols and then deciding which of this point was transmitted. Okay, one of these points will be transmitted, right? Okay, correct. And then based on that, okay, once this is decided, let's say in this case, because this is what will give you the nearest distance. Okay, right, and then you will do the demap the symbols into bits. This mapping, demapping is known. What is not known is, what is demodulator needs to decide is basically whether this point was transmitted or any of these 4 points were transmitted. And there is a rule now. I have given you the rule. Okay, this is the nearest distance rule. Okay, correct. And this is called maximum likelihood decoding. I am not going to the details of this, but that's what it is. Okay, fine. So that's how it is done. That's the job of demodulator. What has demodulator given you now? Bits. Correct. Okay, and those bits you process, and you do the reverse processing at the receiver. Okay, what is the reverse processing you need to do? The demodulation is done. Fine. Okay, then instead of scramble, you have to descramble those bits. Okay, how are you going to descramble those bits? So what do you need to descramble? One thing is that these demodulated bits. There's something else you need to descramble, and what is that? C, pseudo-random sequence. Okay, so receiver has to generate that pseudo-random sequence, exactly the same pseudo-random sequence which is generated by the transmitter, and that information is known to the receiver also. Okay, right? Otherwise it will not be, see, it will fail. If receiver does not have that information, it will fail. Okay, because if you use a different pseudo-random sequence, it will give you a completely different output. Okay, so that information, which pseudo-random sequence to use, that is passed by the base station to the user. Okay, through some other channel, this is called control channel. We'll study that also. Okay, but for this processing, what we are assuming here is that that sequence is known. Okay, right? So what is this? These are scrambled bits. Okay, and scrambled bit output was B tilde. Right? This is what this demodulated output is going to give you. It is not going to give you B, it is going to give you B tilde. But this is right. But you need to unscramble them, and you need to get B from this. How will you do that? Okay? How will you do it? You scramble, you have this B tilde, right? Correct? This is what we have. This is what this demodulated output will give you. What will I do? I'll again XOR with the same sequence. Correct? Okay. So what happens here? So what is, if you substitute, we'll see how will you get B of, because what is happening here? Okay. B of I is B tilde of I. I'm writing it like this. Okay. Right? We substitute it here. I think if I have explained it in the next slide, I will not do it here. Okay, I will just write it here. Okay, so what happens here? If you substitute B tilde over here, okay, how it becomes equal to B of I? Do we understand this? Okay, I am writing B of I is B tilde of I XOR with C of I. Okay, now let's substitute what is B tilde of I. Let's not assume that this is equal to B of I. What is B tilde of I? This is B of I XOR with C of I. You are again XORing it with C of I. Correct? Okay. Now, so you are XORing, let's say, so what is this? I look at it like this. C of I XORed with C of I. What will you get? a bit stream of zeros. Because you XOR the same sequence, XOR the sequence with itself, you will get a string of zeros. Correct? Okay, so what is happening? B of I XORed with a string of zeros, which is of the same length of B of I. What will happen? B of I. You XOR anything with 0, you get back the same sequence. Okay? Right? So this is B of I. That's how you get this B of I. Not okay? Correct? So that's the idea. Okay, you XOR with the same sequence, and that's why you need C of I to be known at the receiver. Fine? Okay? So this is the example. If you have understood that math, this is very simple to understand. Okay, so 8-bit coded sequence B of I, this is C. Okay, so you get B tilde is this. You XOR, what is B tilde? B of I XOR with C of I. Right? Okay. So what you get here is 0 XOR with 0 is 0, 1 XOR with 1 is 0, 0 XOR with 1 is 1. This is a scrambled sequence. How will you get descrambled sequence? You scramble it with again C of I, and of course you will get back B of I. That's what I showed you in the last slide. Because C of I XORed with C of I is 0, and you will get back the same sequence B of I. Simple. Whatever you did at the transmitter, do the same thing at the receiver. Okay, but then scrambler has met its objective, which is basically that it maintains average energy constraint. Done. Descrambling also done. It is exactly the same as the transmitter. Okay, right? So what is the next module which follows after that? So you look at this. There is no notion of code blocks. Correct? Okay. Right, but what follows after this is everything is basically happens in terms of code blocks. There should be this code block segmentation module, which is basically this, right, which should come here. Why it should be there? Because what is segmentation doing? It is deciding what is the size of each of the code block. You need those numbers, right? Okay, you need those filler bits. Okay, and the number, all these numbers you should know. Okay, so what did code block concatenation do? Okay, rate matched codes they are concatenated. Okay, now you need to segment them. Okay, and segmentation is basically you should know E, right? Because what did you do? You put C code blocks of size E together. So you should know C, you should know E, you should know G. Who is going to give you all these numbers? Segmentation, right? So receiver should exactly have the same control information. Okay, right? So with that, hopefully that has been done, because that's how it can segment. Okay, so that information needs to be passed on, and that is basically all this information has to be there with the receiver. Okay, you see how complicated it is. Okay, receiver needs to know all that. Then only it can start this information, this decoding. That's what I said. Okay, the receiver has done all this processing. Okay, then it has this information, then it needs to do this processing. You see how complicated your mobile is. Okay, right? So now, with this, basically you have these 4 rate matched code blocks. Correct? Okay, and this rate is, how much is the rate? This rate is what was asked by the user. Correct? Okay, fine. So we have how many? 4 such rate matched code blocks. Correct? And then this is basically 11340 into 4. Okay, right? So that is G and this is E. Once this E is there, so what is happening? We have to de-interleave. Okay, once this code block has been segmented, we have to de-interleave them. Okay, so this is continuous. So basically what are we doing? We have 4 rate matched code block. Code block segmentation output is 4 code block of length 11340. Okay, total output bit is 45360. This is, again, the numbers remain same. Okay, now this process has happened. You have how many code blocks? 4 code blocks. What do you need to do? De-interleaving, right? What is de-interleaving? You have to look at how interleaving is happening. Okay, you have to do the reverse processing of that. How was this interleaving done? It was interleaved using row column interleaver. What did it do? This. Correct? So you need to know what modulation scheme was used, of course. Correct? Okay. And then what will happen? What are you going to do? what will this deinterleaver do? Okay, it's going to just read them appropriately. Right? You have to write 4 lines of code, read them appropriately. What are you going to do in this case? You take every alternate bit, put it like this. Every alternate bit, put it like this. Then how are you going to read it? You are going to read them like this. Do the opposite of this what you did at the transmitter. That's what is deinterleaving. Right? That's why it's not specified in the standard. None of this is specified. This is, of course, it comes from communication theory. This is basic common sense. Right? Okay, why will anybody specify that? There's nothing to specify here. Okay? Right? So, this is basically, you have done the deinterleaving by reading them appropriately, nothing else. Okay, so deinterleaving is done. This is most interesting. Okay, how is, you have rate match, how you do the rate recovery. That requires some, again, common sense, nothing more than that. Okay, you'll see that. Okay, so what is this common sense? Rate matching, what did it do? What did, either punctured the bits if the rate which was asked by the user is higher, or repeated the bit if the rate which was asked by the user is lower than 1/3. That's what it did. That's all, right? Okay. Now, let's say you look at this puncturing. What is happening? You are not transmitting certain number of bits, right? Which were generated by the rate 1/3 LDPC encoder. As I said, why do you need this rate recovery? Because this LDPC decoder also works at rate 1/3. What does that mean? It will take in n bits and transmit, it will give you k bits. But you have not transmitted n bits. Correct? How many bits you have transmitted? You have transmitted e bits. Correct? Okay? Right? So those e bits, that information, that rest of the bit information is not there at the receiver because you did not even transmit them. Correct? What does that common sense tell you? Because you don't have that information about whether it was 0 or 1. What kind of information you will give for n minus e bits? Some kind of neutral information. Right? Okay, so I'll come back to it, okay, in a second. What is this neutral information? Okay, so LDPC decoder works only for code rate of 1/3, right? Okay, code rate should be reverted back to 1/3 because it works at 1/3. And when I say it reverted back to 1/3, it needs n bits, and so that it can give you k bits. That's what it is. Rate is k by n. Okay, right? How do you generate this rest of the n minus e bits? Do we understand this? Okay, if it is a redundancy version RV0, okay, so you need to implement this circular buffer at the receiver also. Okay, right? So if it is redundancy version 0, right? Okay, what will happen here? How many? If it is, I'll draw this. Okay, how many bits you transmitted? This is n. Right? Bottom is n. This is k. This is what you transmitted. You did not transmit this. Okay, because that's what was asked by the user. Okay, now user will have to decode only using this information. What will it do? You don't have this information. And that's what I introduced the notion of neutral bits. Okay, right? As a transmitter, because what can you transmit as a transmitter? Either 0 or 1. And what is anything in between? If you say, okay, if you fill in these bits with, let's say, 0, what are you telling the receiver? That 0 was transmitted. You are biasing the receiver in favor of 0. If you feed in 1, right, if you write 1, okay, what will happen here? You are biasing the receiver in favor of 1. You are giving wrong information to the receiver. Receiver will understand that 1 was transmitted. Okay. If you write 0 over here, receiver will understand that 0 was transmitted, but that's not the case. What is the case? Then these bits were not transmitted. Okay, right? In order to not bias the receiver, you give this neutral information. What is this neutral information? Half in between. Right? Okay, instead of feeding 0 or 1, you write half. Correct? Okay. LDPC decoder can work with non-binary information. Okay, that's what you have to understand. Okay, so LDPC decoder can work with non-binary information. Okay, so instead of feeding 0 and 1, you should feed half, right? And then you are giving correct information to the LDPC decoder. Any other information is not correct because then you are biasing the receiver in favor of that information. Okay, So that is what I said. Okay. So write neutral bits for bits punctured at the transmitter. Okay. Correct? That is case number 1. What happens for case number 2? When you basically you repeated certain bits also, right? Okay. Correct? So what will happen here is, right? What did you do when the rate was lower than what 1 by 3? What did, okay? Your buffer is only of this length, correct? Okay. This is basically, what is that? N, right? This is K, okay? But you are transmitting more bits than N. So that is what is the rate lower than K by N, right? Okay. K by N is 1 by 3, but if you increase N, right, then the rate reduces. That is what we have learnt. Okay. So, but receiver can handle only n bits. The LDPC decoder can handle only n bits. So what do? You go back and add those bits to what you have already written. There are two different extremes. Okay. One is you did not transmit some information because the rate was higher. Other case was you transmitted extra parity bits, okay, which has reduced the rate, but LDPC decoder cannot handle that reduced rate. It can only work at 1 by 3. How will you revert it back, that lower rate, to 1 by 3? You just combine those bits again at the receiver. Right? Okay? Fine, because user has asked for a lower rate. If you don't do this combining, then you are making your LDPC decoder work at rate 1 by 3. User has not asked for 1 by 3, it has asked for a rate lower than 1 by 3. You need to revert it back to that lower rate. And how do you do that? You simply add those bits. That's the idea. Okay? I hope you get it. Okay? Right? That's, so repeated bits are combined. Okay? Fine. Then what do? You decode it, because what has rate recovery done now? Okay? Let's go back. Okay? So this, feed these rate matched bits, fine, to the LDPC decoder, because it's again 1 by 3 depending on what processing you did here. Okay. So feed these rate matched code block to LDPC decoder, fine, it will give you k bits. Okay. Validate CRC of each code block. There is a code block validation. I have told you how to validate the CRC. Right. CRC of each code block is validated, then validate transport block CRC. If transport block CRC gets validated, file layer job is done. Otherwise, hybrid ARQ will be triggered, right? And then you will go to the again processing. That processing remains same. Okay. Signaling for hybrid ARQ is different. Okay, in the sense that ACK, NAC, ACK has to be sent, NAC has to be sent. That's a part of the control chain. Okay, I'll teach you separately that. Okay, but that's how the receiver processing will be done if everything goes fine. Okay, it goes to the MAC. Receiver has gotten a data. You have gotten your video. Okay, you have gotten your voice, correct? Okay, if not, if it is voice, hybrid ARQ doesn't kick in, right? You will ask yourself to do the hybrid ARQ manually. Okay, you will ask the transmitter to transmit it again, right? What did you speak? Okay, otherwise for data, hybrid ARQ kicks in, and then the same process happens. Okay, so we'll stop here. This is the receiver processing. Okay, we'll continue in the next class. Thank you.